see if this is working. Is it working? Hello, hello, hello. Hello. Alright, I think that's loud enough. I hope it's loud enough. Let's see my volume. Yeah, maybe I just have to turn up, I guess. Well, maybe I can turn this up here. Hello, hello, hello. Nope, I can't. It's full. Okay, cool. So back to what we're doing. Greek. Let's do a lesson on Greek, and then we'll start learning about some machine learning stuff. There. Okay, let me just move this out of the way for a second. It's the first time I've actually remembered to bring it on the screen. Select the correct characters for ZOR. ZOR. Oh wow, this sounds weird. One sec. Sound. What have I done? This sounds so strange. Enhancements. Nope. Mixer. Teach spatial audio. Off. Sound. Ooh. Oh well. This sounds weird. What did you hear? Z. Oh, Z. Okay. Select the correct characters for me. 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 Oh, that's N. So me is that one. Okay. Match the pairs. Zor. Zor. Z. Z. Ze. Ze. An. Me. Ze. The rose. Water. Z. Maria Torisi. Risi. I know this is rice, but I don't think it's got double an I there. Let's see. I thought it might be different. Risi. Maria Torisi. Okay. Yes. Kai. K? I don't know. Tor. Oh. Risi. Oh, it's the Z, sorry. Oh, it's Nai. Okay. The pink. To. Rosa. Mini market. To. Rose. Without the E. Mini market. Me. Yes. So it was Nai. To. Risi. Cool. Alright, that is that. So, cool, wow. Nearly finished this whole part here. Awesome. So, we left off at going through the PyTorch tutorials. Just a little bit of background on where I've been again. I've been doing development on my game, which is a thing I'm doing. I've been learning, watching lectures from Manolis Kellis still. I've been exploring the space of mathematics. In fact, I was particularly interested in Riemannian metrics, the gauge theory, and the fiber bundles that were mentioned in Eigenbro's video. Just a few days ago, I think it was released, maybe even yesterday. So it was funny because I was building up to this point where I'm starting to learn more mathematics. I'm not very good at it still, and then this comes out, and there was this kind of acknowledgement that I'm starting to tie bits together. So it's a very wonderful feeling, and this is all in preparation of getting to grips with the underlying architecture of machine learning data science. And this is all important because once again we're trying to solve some biological engineering issues that I have, which are to do with taking a snapshot of the body and its state so that we can better serve medicine or better live longer, or things like David Sinclair would say, or Brian Johnson. That kind of thing I'm thinking of, and then finally, last thing to say is that to be able to take our bodies or our DNA sequencing to a level whereby it's whereby we can modify it ready for interstellar travel, because I don't know how long this planet's got to live. So we want to be prepared. So that's what we're aiming for. Very big goals. Might be way out of my lifetime, but hey, let's start somewhere. So right, okay. Now to show you how bad I am, let's go to PyTorch. So how crap I am. Oh, actually, episode 10. So we said learn about tensors and their manipulation. Tensors being multi-dimensional arrays, which is interesting. I didn't know it was called a tensor in maths. That's great. And then I've got some points here. You only need to work out the brain because all neurological activity occurs in the brain. Maybe. Copy of nerves, send a pulse through, and use AI to study the patterns delay to account for state. Some of it. Okay, I think that probably wasn't actually covered in the episode, but anyway, let's go here. Copy link. Right. Let's do this. Episode 11. Where do we get to? Gonna be more sure that I share the screen properly this time. Because when I'm watching it back to try and revise, I'm like, oh man, I can't read anything I put on the screen. So tensors, that was the last one, and let's finally just go back to our code. A little recap. How do I collapse all these again? Was that? No, it wasn't that. Collapse all in PyCharm. Control Shift Numpad minus, Control Shift Numpad plus, minus. Alright, cool. So going back through, we have a main and it runs run tensors 2. And then if I go through to that, run tensors 2 is running np.ones 5 t equals torch.from numpy n print n print t. Yeah, I don't quite remember what that does. And what is running before this? Setup, and then run tensors 2. So from numpy n. If I go back to here, what was covered here? At the bottom somewhere. No doubt. Changes in the numpy array reflects in the tensor. Numpy array to tensor. Right. Probably need to recap this, but let's just see if we can push on. So code for processing data samples can get messy and hard to maintain. We ideally want our dataset code to be decoupled from our model training code for better readability and modularity. PyTorch provides two data primitives. The data loader, that's found in the namespace torch.utils.data, that makes sense, and torch.utils.data dataset. So the data loader and dataset that allow you to use preloaded datasets as well as your own data. Dataset stores the samples and their corresponding labels, and data loader wraps an iterable around the dataset to enable easy access to the samples. Okay, PyTorch domain libraries provide a number of preloaded datasets such as fashion mlist, that subclass dataset and implement functions specific to the particular data. Okay, this makes sense. They can be used to prototype and benchmark your model. You can find them here: image datasets, text datasets, and audio datasets. Let's have a little peek at one. Subclass of dataset. They've got getItem and length methods implemented, hence they can all be passed to a data loader which can load multiple samples in parallel using Torch multiprocessing workers. For example, ImageNet data equals to Torch Vision ImageNet path to ImageNet route, blah blah blah, and then data loader ImageNet data, which is this, batch size of 4, shuffle true, num. Okay, all the datasets have almost similar API. They all have two common arguments: transform and target transform, to transform the input and target respectively. You can also create your own datasets using the provided base classes. Well, apologies. Okay, cool. So that's what that looks like. Loading a dataset. Here is an example of how to load the Fashion MNIST dataset from Torch Vision. Fashion MNIST is a dataset of Zalando's article images consisting of 60,000 training examples and 10,000 test examples. Each example comprises a 28 by 28 grayscale image and an associated label from one of 10 classes. We load the Fashion MNIST dataset with the following parameters. Root is a path where the train or test data is stored. Train specifies training or test dataset. Download equals true, downloads the data from the internet if it's not available at root. Transform and target transform specify the feature and label transformations. I assume root means this local path on a Linux computer. I'm not sure. Maybe that's bullshit. Probably is. Okay. So import Torch, get the dataset, get some datasets to Tensor, and then the PyPlot library. Okay. Fashion MNIST data, train true, download true, transform to Tensor. Fashion MNIST. So the training data is simply with train equals true. I see. So downloading from Amazon AWS, interesting. So let's have a little look at that. You won't be able to see this, so let me just zoom in. 7-zip. Okay, extract it there. Yeah. A ubyte file, and a ubyte file looks like okay. That's unreadable. And what is this supposed to be opened with? An unsigned byte or something, is that? I don't know. Extract images from ubyte or let's just see if there's any images. Okay. Might have to look at that later. So anyway, downloads this to zip, extracting, downloading, zip to data raw, okay, downloading. So this is training images, and then this is not talking about training. Okay, cool. Iterating and visualizing the dataset. We can index datasets manually like a list. Training data index. We use matplotlib to visualize some samples in our training data. Labels map equals this. Okay. And then labels map figure equals plot.figure. Figure size 8 by 8. That's not referring to that. Cols and rows equals 3 and then 3. For I in range of columns times rows, 9 plus 1, 10. From 1 to 10. Sample index equals torch.random integer from the training data, which is where training data was here, and then size equals 1 dot item, okay, image label equal training data from the index chosen randomly. Figure is a whatever this does. Add a subplot. Rows is here of rows and columns 3 by 3, and then I would be the index 1 to 10. Plot title of it. Oh, PLT is what again? PLT is... Oh, I've lost track of that. Oh, okay, so PLT is the library. So dot title. What is PLT though? PyPlot. Okay, so plot the title of the labels map. And label maps come from here, right? And you go and get the label because it's now the result of the training data taken from the randomized index, okay? And then turn the axis off, and then show the image, squeeze it, whatever that means, and then okay, so this is a drawing thing, I see, and then show the thing. So we'll get this. Okay, cool, that's nice. Let's just do it then. I see. Is there a way to clean these up, I wonder? Refactor. Maybe, who cares? I guess it doesn't even matter if I duplicate them. Doesn't care, does it? No, it doesn't. Okay, cool. And then I want to declare my training data. So I'll call this. This was dataset and data loaders. Dataset and data loaders. Whoops. Cool. And this is going to be a fashion mnist. Yeah, that's interesting. We just leave it like that. Okay, and then we're going to lay out our data. So we have some labels for them. And run it. Okay. And I think I need to put run here. Nice. Let's get rid of that and see what happens. So it's drawn an image, and then the offset is where it's from. Add subplot rows, columns. Plot.figure. Let me just see this. It's an if you're creating many figures, make sure you explicitly call close on the figures you are not using, because this will enable PyTorch to properly clean the memory. Oh, it's nice to see. Create a new figure or activate an existing figure. What is a figure? Purpose is to create a figure object. The whole figure is regarded as the figure object is necessary. What is a figure object? The top level container for all the plot elements. The figure instance supports callbacks to callbacks. The events you can go. Okay, well I guess the figure means illustration. And this index is some built-in part of this subplot. Okay. So what we've done is downloaded some images, data sets, and we are actually looking at the training data. Yeah. So I wonder what the actual data looks like. So let's do this, and instead of training data, we'll do test data, or the testing data, sorry. Yeah. Let's see what that does on main. Okay. Don't they look any different? I don't think so. Not sure though. And this is the grey because it's been forced to grey. Okay, understood. Right. Creating a custom dataset for your files. A custom dataset class must implement three functions: init, length, and get item. Take a look at this implementation. The fashion mnist images are stored in a directory image.dir, and their labels are stored separately in a CSV file, annotations file. In the next sections, we'll break down what's happening in each of these functions. So here's our class inheriting from the dataset. We're overriding we're giving it a constructor. We are reading from an annotations file from the CSV. We are locating where the images are coming from. Don't know what that's doing. I don't know what that's doing, because it doesn't have types, so I'd never know. And then the length is just returning what we've declared as the CSV output. Okay, but I guess it's a function of, so we can do whatever we want. And then get item is taking an index and joining the directory with the labels index location, reading the image from that path, and then getting the label for it. And if transform is on, then transform the image. If target transform, then target transform label. That's interesting. And then return the image. Okay. And the label. Is that as an object? I don't know Python that well. The let's just do that then. So I'm going to call this fashion data set. .py. Oh, we might. Okay, fine. So we don't actually have this data, so it's just giving us an example. Okay, I got you. The init function is run once when instantiating the dataset object. We initialize the directory containing the images, the annotations file, and both transforms, covered in more detail in the next section. The labels.csv file looks like this. So an image, other stuff, and then, okay, that's interesting. Yep, okay. And then the length function returns the number of samples in our data set. Yep. And the get item function loads and returns a sample from the dataset at the given index. Based on the index, it identifies the image's location on disk, converts that to a tensor using read image, retrieves the corresponding label from the CSV data in image labels, calls the transform function on them, if applicable, and returns the tensor image and corresponding label in a tuple. Preparing your data for training with data loaders. The dataset retrieves our dataset's features and labels one sample at a time. While training a model, we typically want to pass samples in mini batches, reshuffle the data at every epoch to reduce model overfitting, and use Python's multiprocessing to speed up data retrieval. Data loader is an iterable that abstracts this complexity for us in an easy API. Okay, so import from the data loader, and then we create data loader, which is our instantiate data loader with some training data, a batch size, and then shuffle true, and so on and so forth. Iterate through the data loader. We have loaded that dataset into the data loader and can iterate through the dataset as needed. Each iteration below returns a batch of train features and train labels containing batch size 64 features and labels respectively. Because we specified shuffle equals true, after we iterate over all batches, the data is shuffled. For finer grained control over the data loading order, take a look at samplers. Let's have a little peek. Display image and label. So both of these equals next iterate on the train data loader. Print the size, squeeze image. Yeah, I don't know what that is. Yeah, I guess it's just fit the image in the grid. Label from 0, image show, plot show, and then print the label. I see where we're going with this. This is analyzing the pixels, so we're having to investigate what we're having to label, or we're having to comprehend color with, or yeah, label color with a coordinate. Okay, great. So let's do that then. So we've got our, but we don't have those datasets. Okay, so oh, that's it. Okay. So we'd better get that data. I wonder if it says it up here, if I can get it. So we're importing it, and then iterating it, and creating a custom dataset for files. Take a look at this installation. Directory. Okay, well, let's just go on. Transforms. Right, what's the time? Cool. Haven't been on for much, have I? No, half an hour. Cool, okay. So, data does not always come in its final process form that is required for training machine learning algorithms. We use transforms to perform some manipulation of the data and make it suitable for training. All Torch Vision datasets have two parameters: transform to modify the features and target transform to modify the labels that accept callables have two parameters that accept callables containing the transformation logic. The Torch Vision Transforms module offers several commonly used transforms out of the box. The fashion in this features are in PIL image format, and the labels are integers. For training, we need the features as normalized tensors and the labels as Hot Encoded Tensors. To make these transformations, we used to tensor and lambda. So there's two things I didn't understand there. PIL image format. Mm. The Python imaging library PIL supports a wide variety of raster file formats. Over 30 different file formats can be identified and read by the library. Write support is less extensive, but most common interchange and presentation formats are supported. Okay, so it's an Python imaging library. Gotcha. And the other one was Hot Encoded Tensors. One hot tensor is a tensor in which all the values at indices where I equals j and I does not equal j is the same. It's a tensor in which all the values at indices. So let's just try and understand that. Let's take a tensor. Where, okay, I equals j. Yes. Oh, it's got it here. Great example. This method accepts a tensor of indices, a scalar defining depth of the one hot dimension, and returns a one hot tense, or with default on value 1. This is terrible. And returns a one hot tens, or with default on value 1 and off value 0. These on and off values can be modified. Initializing the input, printing the input, generating one hot tensor, printing the results. So here's our input 1, 2, 3, shape 3, 1, type of integer 32, and our result of that is 0, 1, 0, 0, 0, 1, and 0, 0, 0. This example explicitly defines the on and off values for the one hot tensor. Okay, so this is going to need another one. I'm guessing I, J, K, and then it says in which all the values at indices where I equals j, index equals j, and index does not equal j is the same. So that means that when the index is... Oh, no, I don't understand that. Don't understand it yet. This example explicitly defines the on and off values for the one hot tensor. So initializing the input 1, 2, 3, printing the input 1, 2, 3 with the shape 3, and then generating one hot tensor. Takes the indices, gives it a depth of 3, an on value 3, and an off equals -1, printing the resulting tensor. Means on value equals 3, off value equals -1. Oh, I see. That means that when it's getting to this notational requirement, these are the values that it uses to denote the on and off state of this thing. It's too abstract. Let me go one more. TF1 hot. There we go. I'm currently doing a course in TensorFlow in which they use tf.1hot indices and depth. Now I don't understand how these indices change into that binary sequence. Oh, is that a binary thing? Is that what that is? What number is binary? Binary to numbers. Two. 001 1 000 1 oh 0 1 2. The input is 1 2 3. Shape is 3. Take the indices to the depth, generating one hot tensor. A one hot tensor. So one would become. Okay, let's go back to this. Great. Not too sure what that's doing at the moment. So suppose you have a categorical feature in your dataset, e.g. color, and your samples can be either red, yellow, or blue. In order to pass this argument to a machine learning algorithm, you first need to encode it so that instead of strings you have numbers. The easiest way to do such a thing is to create a mapping, almost like an enumeration, and replace each string with its mapped value. However, this might create unwanted side effects in our machine learning model, as when dealing with numbers, it might think that blue is greater than yellow, because 3 is greater than 2, or that red plus yellow equals blue because it's 3. The model has no way of knowing that these data were categorical and then were mapped as integers. The solution to this problem is one hot encoding, where we create n new features, where n is the number of unique values in the original feature. In our example, n would be equal to 3 because we have 3 unique colors, red, yellow, and blue. Each of these features be binary and would correspond to one of these unique values. In our example, the first feature would be a binary feature telling us if that symbol is red or not. The second would be the same thing for yellow, and the third for blue. An example of such a transformation is illustrated below. So red would be 1, yellow would be where we create n new features where n is the number of unique values in the original feature. Yep. Each of these features can be binary and would correspond to one of these unique values. In our example, the first feature would be a binary feature telling us that the sample is red or not. The second would be the same thing for yellow, and the third for blue. So red is 1, yellow is 1, green is 1, yellow should in that case be wait, that's red, yellow. Okay, whatever. Note that because this approach increases the dimensionality of the dataset, if we have a feature that takes many unique values, we may want to use a more sparse encoding like the one I presented above. Okay, so let's go back to that. So it's saying that one. I think it's actually one hot is generated it for us. I think that's what it's trying to say here. It has denoted that there are 3 different indices, and it has, by using the number 1, generated unique values for them. So I guess if you were to say a shape of 4, that would be wasteful. Okay, there's just a couple of guesses here, but yeah. Oh, you can't see any of this. I'm so sorry. Okay. Really speaking to myself because I'm the one who looks at it after. Okay, so now to the second example. Constant 1, 2, and 3. Printing the input of indices, and then it does 1 hot, but it's saying the on value of it is rather than 1, it's 3, and the off is -1. Okay, that's really interesting. Oh wow, that is really interesting. Cool. Okay. So let's look at this. So to make these transformations, we use the tensor and lambda. So it says labels need to be 1 hot encoded tensors. Okay. So go and get the root from our fashion MNIST data. Get the training data. Transform it to a tensor. And the target transformation that it's going to take is the lambda expression of 1 hot. I guess that's the 1 hot part. And it's going to be torch, float, scatter. Hard to tell what that does, I think. So it downloads it, doesn't say anything about that. To tensor converts a PIL image or NumPy n-dimensional array into a float tensor and scales the image's pixel intensity values in the range 0, 1. Lambda transforms. So, okay, converts a PIL image or NumPy n-dimensional array into a float tensor and scales the image's pixel intensity values in the range from 0 to 1. Lambda transforms apply any user-defined lambda function. Here, we define a function to turn the integer into a 1 hot encoded tensor. It first creates a 0 tensor of size 10, okay, the number of labels in our dataset, we now know that, and calls scatter, which assigns a value of 1 as the which assigns a value equal to 1 on the index as given by the label y. So we're going through our data and we're creating 10 because it's that big, or it has that many items in it, and the type will be float. Scatter, which assigns a 1 on the index as given by the label y. So scatter, dimension 0, index equals torch.tensor y. So feed in that, the value 1. Torch tensor is a multidimensional scatter. Writes all values from the tensor src into self at the indices specified in the index tensor. Okay, that makes sense. Interesting. Build model. Build the neural network. Neural networks comprise of layers, modules that perform operations on data. The Torch NN namespace provides all the building blocks you need to build your own neural network. Every module in PyTorch subclasses the NN.module. A neural network is a module itself that consists of other modules, layers. This nested structure allows for building and managing complex architectures easily. In the following sections, we'll build a neural network to classify images in the fashion MNIST dataset. We want to be able to train our model on a hardware accelerator like GPU if it is available. Let's check to see if torch.cuda is available, else we continue to use the CPU. Right, I'm not going to go any further on this. This is great. This makes complete sense. This also makes sense. And I have to say, thanks to this and to this. So whoever you are, thank you so much. That was wonderful. No, not this one. This and this. So yeah. Thanks all. I will continue this. I'm going to put a little bookmark here. And just summarize what I've learned in this episode. So we got to here. We learnt that a one hot tensor is where categories are labeled in a binary sense. One hot tensor is where categories are labeled in a labeled in a binary sense, so that they are specific. They are not able to be confused. So, how do you word this? We learned that a one-hot tensor is where categories are labeled in a binary sense. Red equals 0, 0, 0. Blue equals 0. Green equals 0, 1, 0. Blue equals 0, 0, 1. The reason is to avoid confusion of enumeration categorization, where if red equals 1, blue equals green equals 2, blue equals 3, 1 plus 2 may may confuse the tensor into confuse the machine learning algorithm to think it is looking at blue and not red plus green. Cool. We learnt about inheriting from data set. I think it was that. It was, yeah, data set, in order to write our own training model and to write our own data set where underscore init length and, well, inner length and get item are virtual methods to override abstract methods to define. What else did we learn? We learned that we can use plot plt library to plot graph. We can use pyplot library to plot a graph. We can use what else was it? Image, yeah, okay. We can use pyplot library to draw images on the above graph, to assign color values to coordinates, and we also, yeah, preparing, cool. We also learned this transforms. That was it. Okay, cool. Yeah, nice. Well, that's cool. So it's interesting that I mentioned the like Riemannian metric. You know, I don't know what that is yet, but I realise that it could be it's a metric, a mathematical tool. Metric being like egg, sausage, time, speed, and in the Riemannian sense, it's clearly it has more kind of function. But I find it interesting that we're doing this because you could imagine, rather than plotting coordinates for an image, you may need to think in a kind of abstract, multi-dimensional or n-dimensional space, and this is the kind of thing. So a multi-dimensional space, and not only just categorize or stick with, like, if something needs a metric per coordinate on a 2D plane, then that metric would need to be a function, and that function is called a it is part of gauge theory and the fiber bundling. And you can see, interestingly, that, well, I can see reasons why you might need to do that kind of mathematics for analyzing data. That's kind of cool. That's really nice and so thank you, Eigenbros, for getting Tim on. Tim, sorry, my apologies, I can't quite remember the name. Let me just get that, because it's really important, because that was just the best thing I've ever watched. Yeah, Timothy Nguyen. So thank you, guys. Thank you so much, and I'll continue this very shortly. So bye for now.